Okay, we have the next topic, mathematical induction. Alright, this is a way of proving something. So, just to start off, I'll just go over a little bit about proofs. So, don't worry if you're in my class about writing this down for the moment. Just have a listen. So, for example, sine squared theta plus cos squared theta equals 1. Like if you were trying to prove that, one way that wouldn't work to prove it is to just pick an example number. Okay, if I picked my angle is 30 degrees, I can show that sine squared of 30 plus cos squared of 30 does equal 1. Okay, so I can show that that is true for one example, but that's not a proof. A proof has to somehow include all possible values. Okay, so one value is not enough to prove something. And so just a second example, something slightly different. If I have sine squared theta, this is plus sine squared of 2 theta equals 1. Okay, so this is my proposition. This is something I'm trying to prove. Again, I could show one example where it is true. Okay, where theta is 30 degrees. So it is true, but of course that's not a proof. If I pick theta is 60 degrees, and I work through that, I end up getting 1.5 for my answer. So that one example is enough to prove that it is not true. Okay, so one example can't prove that it is true, but it can prove that it is not true. So just quickly, let's look at this Pythagorean theorem. You may not have seen. You've been using this since grade 9 or so, and probably just accepted it, but you've probably never been shown why this is true. So let me just show you quickly. Here, if I have a diagram with my triangle A, B, and C, I can extend this diagram a bit. You can do a giant, large square and make several other equal triangles here. A, B, C, A, B, C, A, B, C. So if I look at these areas of these different squares, here let's say here's my shape, here's my area. So the large square, the area of that is A plus B, which is one side is A plus B squared, which is A squared plus 2AB plus B squared. I've got a small square, which of course these are all going to be 90 degrees in here, so this is a square, so this is just C squared. And I've got 4 triangles. And each triangle, I've got 4 times each triangle is half base times height. So, of course the 4 triangles plus the small square have to equal the large square. Or other way around, a squared plus 2ab plus b squared has to equal 2ab plus c squared. Cancel the 2ab, and there's your Pythagoras. Proved. So that's the sort of geometric way to prove something. Okay, so now let's get into what this topic is, this chapter, and it is proof by mathematical induction. So another completely different way to prove something. So we start off, we call it P of n, we have a proposition. And it can be for any natural number. So just skipping down for a sec, just have a look at my proposition here in an example. Here's an example of a proposition. The sum from 1 to n of 1 over 2r equals this. Okay, that would be my proposition. Alright, so a proposition is true for any number, any natural number n. So n can be any number 1, 2, 3, 4, and so on. So the principle of mathematical induction states this proposition is true if two things are true. Two things have to be true. It has to be true for the first number. Okay? We always start at 1. Well, it could start somewhere else, but it has to have a starting point. All right? For the first number, it has to be true. The second, this is the important, difficult part, is that whenever p of some number k is known to be true, this must imply that the next number, the proposition must be true for the next number, p of k plus 1. Alright, so this is telling us, for example, if we know that the proposition is true for 1, then that tells us the proposition is true for 2, and so on. If the proposition is true for 4, then we know that the proposition is true for the next number 5. And if you can prove this in general, so that for any number, if any number is true, that means that the next number is true. That lets you sort of prove it. So the way of looking at it is a ladder. Okay, we prove that the first number is true. And if we know that, if we can prove the second point, then one number true implies that the next number is true, which implies that the next number is true, which implies that the next number is true, and so on, so that you've automatically proved it for every possible number. Alright, if that's a bit confusing, let's do an example and put it in action here. So here's the example. Here's our proposition that we need to prove is true. Okay, so this is sort of written like a function, proposition in bracket n, and here's n several places in this statement. Okay, so this is a statement. Alright, so what is the statement? Let's look at these steps here. So what is the statement p of 1? It's basically just in this formula changing all the n's to be 1's. Okay, so down here, a. Instead of n everywhere, I'm going to write a 1. Okay, that's my statement for 1. What is the statement p of k? Or what is this, putting a k there? And the same, k plus 1, I put a k plus 1 here. So, there's a couple of things. When we're doing the proof, this is something we sort of assume true. Because if we know that this one is true, we need to then use it to prove this one here. Okay, this is what we have to prove. Alright, next one. How can the sum from 1 to k be changed to the sum of 1 to k plus 1? Okay, this is sort of one of the techniques for doing it. So we've got r is 1 to k, or 1 over 2r. So what this means is that this is the 1 to k means I'm adding together. I'm adding the first term, I'm adding the second term. So when r is 1, that's the first, 1 over 2 to the power 1. The second is 1 over 2 to the power 2. So I'm adding these all up, plus the third, and so on up to the kth. Okay, that's what that means. And the other one, and it's k plus 1, 1 over 2 to the r. So this is the first plus the second plus the third plus dot 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 plus the kth plus the k plus 1th, however you'd say that. So, question D said, how do you change this into this? Well, basically, we've just added, all we've done is take that and added on this k plus 1 term. Okay, so this is saying that this, to get this, we've just taken what we started with, r equals 1 to k of 1 over 2r, and we've added on the k plus first term, which is when r is k plus 1. So 1 over 2 to the k plus 1. Alright, which is, again, we have assumed true that this thing here equals, up here we've assumed equals this. Okay, so we could also write this 2 to the k minus 1 over 2 to the k plus 1 over 2 to the k plus 1. Okay, so that's how we change this one into this one. Alright, so for part E, now comes the proof. Use the principle of mathematical induction to prove that the original statement is true. Okay, so P1 must be true. So is r equal 1 to 1, 1 over 2r equals 2 to the 1 minus 1 over 2 to the 1. That's basically part A. Is this true? So true. Well, you can easily check. It is on the left side, it's just 1, is a sum of one number. It's just 1 over 2 to the 1. And that equals 2 minus 1 over 2. And that is true. This there a half equals a half. Okay? So true. So we've proved the first part of the mathematical induction. So the second part is showing that that if pk is known to be true, pk plus 1 must also be true. So we're proving, we need to prove this. So we've already got so this left side here, this left side, which is down here, we have got this. Okay, so we need to say, is that, are these things, are they equal? Okay, that's what we need to, just all we need to show, and we've proved it. So is 2 to the k, take 1 over 2 to the k plus 1 over 2 to the k plus 1. Is that equal to 2 to the k plus 1 minus 1 over 2 to the k plus 1? Is that true? Okay, we need to make a common denominator to add fractions, and to do that all we need to do is times by 2 top and bottom. So we get 2, expand this, 2 to the k plus 1 minus 2 over 2 to the k plus 1 plus 1 over 2 to the k plus 1. Okay, which equals, so we're just coming down here the left side of this, and that is going to be equal to 2 to the k plus 1 minus 2 plus 1 is minus 1 over 2 to the k plus 1. Okay, which is, that is equal. So we've proved it. So we can say now, thus, sum r equals 1 to k plus 1, 1 over 2r does equal 2 to the k plus 1 minus 1 over 2 to the k plus 1. So by the principle of mathematical induction, the proposition that the sum that we were trying to prove is true for all values of n. So we just proved it for every single value. So just an example for you to try down below. Prove that this sum on the left equals this total on the right. So give that a proof, and just, if that confuses you a bit, that can also be written as this sum. Okay, I'm almost at my 15-minute time limit. We're done.